Hey, today we're going to be talking about lesson 3.9, which is inverse trig functions. As with all functions, when we talk about inverse functions, we swap the input and the output. So here we go. The inverse of a trig function is the result of switching the input and the output values of a function. So as a result, the output value of an inverse trig function will always be the angle measure. All right, it's going to be good practice here to go ahead and highlight that, okay? The result, the output value of an inverse trig function will always be an angle measure, all right? Meaning that's going to be our answer, all right? So here we go, notation. We can represent inverse trig functions two different ways. On the AP exam, you might see either one of these, okay? One of them looks like it has a sine to the power of -1, and then the other one just says arc sine. Both of them mean inverse trig function of sine, okay? With either notation, though, we would read them as arc sine of x. Some people read inverse of sine, but we could read them as arc sine of x, okay, when reading it aloud. So here we go. Let's do the first example. Let's write the statement sine of pi over 6 equals to 1/2 with the equivalent form using arc sine notation. Well, since we know that the answer will always be the angle measure, what we want to do here is swap the input and output. And of course, writing arc sine notation. So there's two ways to write this out. We could write this as arc sine of 1/2, which is going to equal to pi over 6. And the other way is we could write it as arc sine of 1/2 again, but we'll use the other notation here, which has that exponent of -1. And that's also going to equal to pi over 6, okay? So either one of those is the same thing, but that's how we would write it as an inverse trig function, all right? Now, because trig functions are periodic, there's a restricted domain that creates the corresponding inverse trig functions. All right, so let's talk about those restricted domains. Here we go. You can see with the sine function, right, when we talk about the inverse sine, all right, that's our arc sine, we see here that this is the restricted region, okay? Now that goes from -pi/2 all the way to pi over 2, okay? So let's put here -pi/2 all the way to pi over 2. And of course, it goes in this rotation here. Just because that's the way the interval is written. Okay, so now we have also the inverse of the cosine function, right? Our cosine. And that one goes from 0 to pi. Okay, so here we have our 0, and here we have our pi, and that goes in this rotation here, okay? Again, just because the way the interval is written. And then we have inverse of the tangent function, and that's what we call arctangent, okay? And that goes the same way as the sine, right? Except we say, same way as the arc sine, except it goes from -pi/2 to pi over 2. And this time, notice that there's a parentheses instead of a bracket. It's an open interval, which means that we don't want to include these 2 points in that interval, okay? But it's still going this way, all right? So we're going to keep that in mind as we write out these values, okay? So we need to remember a little bit about the unit circle here. Let's review. And so for the unit circle, you might remember that there's a quadrant 1 that was a hot topic, right? The radius of the unit circle is 1, and so that's why this coordinate here was, 1, 0. And of course, this coordinate up here was 0, 1, okay? This angle was pi over 2. This angle here was 0. If we go all the way around, we get that 2 pi, right? And of course, there were other quadrants. Okay, so with that being said, 3 common angles that we always worked with. We had that pi over 6, we had that pi over 4, and we had that pi over 3. Okay, and so we always count up. So here's our 0. Let's just count up. So we got the square root of 0 over 2, the square root of 1 over 2, the square root of 2 over 2, the square root of 3 over 2, right? That's our x's. Now we go with our y's, right? And we're going to count up from there. So square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and boom, right? Okay, so there we go. We got our cosine values, our x's, our sine values, our y's, because our unit circle has a radius of 1, okay? So let's answer those questions that we saw over here. Okay, so here we go. I went ahead and put that unit circle on the same slide where I have the questions. So since we're working with the arc cosine, we're going to try to get an angle here that's on this restricted region. And you can use that all students take calculus. That would be helpful. But on this restricted region, I want to focus on where cosine is going to give me a negative value, but also still square root of 2 over 2. And I know that I can use this radical 2 over 2 to help me. So the reference angle that's the reference angle, pi over 4. But I'm going to be using the angle that's in quadrant 2 because cosine is negative in quadrant 2. All right. So I'm going to say that the angle that goes over 4 here in quadrant 2 should be 3 pi over 4. Okay. And that 3 pi over 4 does in fact fall from 0 to pi. So this here should be 3 pi over 4. Okay. The next question is here. We have the arc sine of negative radical 3 over 2. Now I notice that this is a negative, so that's important. But where do we get a sine value of radical 3 over 2? And I see that happening right here at the pi over 3. Okay, so since the inverse sine has that restriction from negative pi over 2 to pi over 2, and I see that happening right here at pi over 3, that's important. But this is where all the functions are positive, right? Okay, so that means that down here is probably where I want to find my answer, right? Except I'm going to use that angle that goes over 3 because that's the one that's going to have the same radical 3 over 2 sine value, right? Except it's probably going to be negative down there because why? Well, because in this quadrant down here on the bottom, right, quadrant 4, cosine is positive, but sine should be negative. And that's how we're going to get that negative radical 3 over 2, okay? And so our answer there should technically be this angle. However, I want to write it from negative pi over 2 to pi over 2. So instead of saying, oh, this is 5 pi over 3, I want to kind of keep it within this region here. So I'm going to say that this goes down, the same way this goes down to negative pi over 2, well, this can go down to negative pi over 3. And so that's going to be our answer there, negative pi over 3. All right, and then over here, we have arc tangent of radical 3. So we got to think about when we get the tangent value of radical 3. Well, you might remember that tangent is basically just y over x. And so if I take this y value and I divide it by this x value, I'm going to get a tangent value of square root of 3. Over here on this coordinate of pi over 4, if I take this y value and divide it by this x value, I'm going to get a tangent value of 1. And then over here, if I divide 1/2 over radical 3 over 2, that's y over x, I'm going to get a tangent value of square root of 3 over 2. Okay, so now that we have that, we are able to figure out where we have a tangent value of the square root of 3, right? So that appears to be here at that pi over 3 again. Perfect, right? Okay, that's here. However, I do want it to be positive, right? I want it to be positive. All functions are positive here, right? Remember, all students take calculus and all functions are positive here. The only thing that's positive down here is cosine, and I need the tangent to be positive. So that's perfect. That's the angle I want to go with. So I'm going to go ahead and write here pi over 3. All right? Okay, so that talks a little bit about the restrictions. Now, this is another type of question that could be kind of tricky. Okay, we're going to go through it and piece it together. It says here, angle theta is in standard position. And that's this one right over here, okay? Angle theta is in standard position. The terminal ray intersects the unit circle at point P. Here that is, point P right there, okay? All right, coordinates of that, x, y. Now the points Q, R, and S are the results of the terminal ray being reflected over the y-axis, over the origin, and of course over the x-axis, okay? So for each of the following expressions, determine which labeled point intersects the terminal ray of the given angles. So what do we have to do here? Let's see. For each of the following expressions, these are different questions, okay? Determine which labeled point. Oh, so we just got to figure out which point goes. Which point intersects the terminal ray of that axis? Okay, perfect. We got it. So here I'm seeing the arc cosine of x. Okay, well, let's think about this. Arc cosine of x had this restricted region right there. And it says arc cosine of x. I don't see any negatives there. I don't see any reflections, which means that if I'm going to keep that point exactly where it is in this region without making any reflections, I'm going to keep it right there where it's at. That should be point P. So we just got to go ahead and say, determine which labeled point intersects the terminal ray of the given axis. So basically identify where the points intersect the terminal ray. Let's do question C. Okay, we said this was the restricted region for the arc cosine, right? Okay, now if I'm seeing a reflection because of that negative x, that means the point can't be here. All of a sudden now it's going to bounce over here to the other side, which means the point is going to get forced to have that reflection, and it's going to now be at point Q. All right. All right, so hope that helps. Now let's go ahead and erase, and we can go ahead and see what happened, or we just use another color. How's that? We'll use another color, and we'll see what happens now when we do the inverse sine. Now you might remember that the inverse sine and the inverse tangent had a very similar restricted region, right? Both of them went from negative pi over 2 all the way to pi over 2, right? The only difference was with the inverse tangent, we did not include those two numbers, okay? All right, so let's start with the inverse sine. The original point did fall here, right, at point P. So arc sine of negative y. Okay, so since that's the restricted region, right, this bluish region there, right, focus on that. If that's the restricted region, and the original point was here, I see a negative, that means reflection. Ooh, now I'm going to go ahead and bounce over to the other side and reflect that. So now that's why we're going to go ahead and say it's just going to fall on point S. And then for the inverse tangent, these could be a little trickier. All right. I notice that tangent without a reflection would in fact be at the same point as well. Okay. Because we know that all students take calculus, right? So that would be a positive y over x. Now, the moment I say, hey, wait a second, let's apply a negative to that, well, then that means that we're going to bounce down here to get that negative tangent value, because all students take calculus. The only place we have positive tangent values are here and here. We have negative tangent values here and here. The thing is, we have that restriction, right, which forces it into this quadrant. Okay, so that means it's going to be forced into point S. Okay. All right, so that's kind of how that works. And that also wraps up lesson 3.9. I hope that wasn't too tricky. You're going to get a chance to answer some practice questions to make sure you have a solid understanding of these inverse trig functions.